You are listening to The Vocal Technologist. Spoken tech for your ears.
So, picture this. Back in December 2025, a developer asked their local AI coding agent to just, clean up some redundant files.
Right, a super standard task.
Exactly. But seconds later, their entire Mac home directory was gone. Just wiped.
Oh, wow.
Literally completely erased from existence, all because the AI blindly executed an r-apt-area-f command with a trailing ~/. And the crazy thing is, today, we are handing the keys to our enterprise cloud infrastructure over to those very same AI agents.
Yeah, it really puts things in perspective.
It does. So welcome to another deep dive. Today's mission for you, the learner, is to cut through all the noise of the early June 2026 TLDR DevOps dispatches and, extract the actual signal.
There's a lot of noise out there right now.
There really is. We are unpacking the reality of modern infrastructure. We're handing the blueprints over to these autonomous multi-agent systems it's brilliant. It's completely transforming how we work. But simultaneously, it's incredibly expensive and sometimes just terrifyingly insecure.
Seeing all these sources synthesized together really creates a stark picture. I mean, I love the visual we have running in the background today.
Oh, the command center.
Yeah, that blend of a glowing, high-velocity digital command center anchored by those towering classic bookshelves. It just perfectly represents the tension we are exploring today.
I totally agree.
We are essentially bolting this bleeding edge, entirely unpredictable artificial intelligence onto foundational, decades-old principles of computing.
Okay, let's unpack this tension, because our first piece of data is it's a massive reality check. I'm looking at this recent IBM survey from the sources, and it notes that 84% of developers are currently using or planning to use AI-assisted programming.
Which makes sense, right? Everyone is jumping on board.
Right, but the picker is that only 3% highly trust the output.
Just 3%.
Just 3%. That gap is just staggering to me.
It really is. And I think the industry is hitting a wall with what the sources refer to as vibe coding.
Vibe coding. I love that term, but it sounds dangerous.
Oh, it is. That's the practice of prompting an LLM to build an entire feature from scratch, glancing at the output, feeling like the vibes are right, and just pushing it to production.
Yeah, that's like letting a teenager drive your car blindfolded just because they sounded confident. If we don't trust the output, why on earth are we letting these agents touch our code bases?
Well, when you lack trust but use it anyway because of the speed, you are basically playing Russian roulette. But the natural evolution away from that exact risk is what IBM and others are now calling agentic engineering.
I want to dig into that shift, because from what I'm reading in the sources on how teams are prototyping with tools like Claude Code, the human role isn't disappearing at all, it's just migrating.
Yes, exactly.
Instead of one massive prompt to build a whole app, developers are designing multi-agent systems. You give the agents these hyper-specific, heavily bounded tasks, like one agent exclusively handles refactoring a specific module.
Right, and another is locked down to only writing documentation.
Exactly.
And that modular approach, it fundamentally changes the daily life of a software engineer. The sources highlight that developers are actually typing significantly less boilerplate code now.
Which I'm sure nobody is complaining about.
Oh, definitely not. Instead, they are spending the bulk of their time architecting boundaries, writing incredibly strict technical specifications, and designing automated tests to validate the agent's work.
So you aren't actually trusting the AI to be right? You are building a system that forces the AI to prove it's right before the code merges.
Precisely.
Which brings us right back to that developer who lost their entire hard drive. Because that agent lacked the contextual boundary to understand that a ~/ means the root of a user's digital life.
It just blindly followed instructions.
Right. And if a local agent can cause that much destruction from a simple contextual misunderstanding, giving these agents access to our enterprise cloud environments has to be a security nightmare. I mean, attackers don't even need to find traditional software bugs anymore. They can just manipulate the AI's logic.
What's fascinating here is how rapidly the threat landscape has pivoted to exploit these new workflows. Attackers are going after the AI supply chain directly now.
Like skipping the app and going for the tools building it.
Exactly. A prime example in our stack of sources is the recent checkmarks compromise. Attackers actually managed to infiltrate official KICS Docker images. And KICS is a super popular open source tool for finding vulnerabilities in infrastructure as code.
Wow.
But they didn't stop there. They also compromised official VS Code extensions that developers use.
Wait, so they embedded malicious code directly into the security and IDE tools developers are using every single day?
Yep. They replaced the official repository tags with trojanized binaries. And embedded inside those was a malicious file called mcpbad.js.
Okay, and what did that do?
Well, because developers are running highly privileged AI agents locally to assist with their coding, this trojanized script was able to piggyback on those exact permissions.
Oh.
Yeah. It quietly exfiltrated cloud credentials, GitHub tokens, and developer secrets. And it utilized GitHub Actions and NPM republishing as part of this highly sophisticated multi-stage attack.
Let's talk about the mechanics of how these agents actually break out of their sandboxes, because the sources point to some pretty glaring architectural flaws. For instance, the OpenClaw framework running on Azure Kubernetes Service, or AKS.
That's a great example to look at.
If I deploy an AI agent in a standard Docker container, the general assumption is that it's isolated, right? But OpenClaw relies on broad system access to even function.
Right. And standard shared kernel containers are inherently leaky if a process has broad access. If an attacker manages to, say, prompt inject the AI or feeds it untrusted skills, the AI can exploit the kernel it shares with the host machine.
So it breaks out of the container entirely.
Exactly. The attacker can execute a container escape, take over the underlying AKS node, and from there just move laterally across the entire enterprise network.
Which basically means standard containerization is dead for AI workloads.
I'd say so, yeah.
I mean, a standard container is basically like renting a room in a house, right? If your roommate accidentally sets the kitchen on fire, you are still in massive trouble.
That's a really good way to put it.
And the sources mention that the mandatory mitigation now is Kata micro VM isolation. You are giving the AI its own detached tiny home. It runs its own isolated kernel. So even if the AI burns its tiny home to the ground, the main server farm remains completely untouched.
That is a perfect way to visualize the compute isolation. But securing the compute layer doesn't solve the network vulnerabilities.
Right.
The Agent Core S3 issue outlined in the sources is a brilliant showcase of network manipulation. Researchers proved that if you give an AI code interpreter access to an S3 bucket, which developers do constantly so the AI can read datasets or output logs, attackers can weaponize that connection.
Wait, I'm stuck on the mechanics of this S3 bucket exploit. If the bucket is locked down securely inside a virtual private cloud, a VPC, and standard DNS exfiltration is blocked, how is the AI communicating with the attacker in the first place?
Well, it actually doesn't need to reach out to the attacker directly.
Really?
Yeah, the attacker uses a different, less secured vector to drop a malicious payload into the S3 bucket. And because the AI is programmed to continuously poll that bucket for new tasks, it just naturally reads the attacker's file.
Oh, I see.
It interprets the malicious instructions, executes them locally inside its sandbox, and then writes the result back into the S3 bucket. Then the attacker just retrieves the result.
Wow.
They have effectively created a bidirectional command and control, or C2 channel, using native cloud storage as the intermediary.
That is incredibly stealthy. I mean, to mitigate that, you would have to enforce brutally strict VPC gateway endpoint policies, ensuring the S3 bucket only accepts traffic from highly specific internal resources.
Exactly. It totally validates the Datadog CI/CD threat matrix we're looking at in the data. The production database just isn't the primary target anymore.
They're moving further up the chain.
Attackers are aiming at the source code management, the CI pipelines, and the deployment layers. They are exploiting the machinery that builds the software because the machinery now has the highest privileges.
It really sounds like we are engineering our own downfall here. We are spinning up thousands of autonomous agents, giving them access to our infrastructure, and actively expanding our attack surface by orders of magnitude. Are we just building our own doom?
I get why it feels that way. The apprehension is completely justified, but the data actually tells a dual story.
Okay, I'm listening.
While AI creates a massive new attack surface, it is also maturing into our most robust defense layer. We are essentially using AI to fight AI.
Show me how, because right now, looking at the sources, it feels like a massive liability.
Well, look at the evolution of DevSecOps with Claude Code on AWS. Traditionally, a human security engineer would have to manually review thousands of lines of Terraform code for misconfigurations.
Which is incredibly tedious, and let's be honest, prone to human error.
Exactly. But now, organizations are deploying AI as an always-on continuous security layer. It uses multi-agent parallel audits.
So you have multiple agents reviewing the same infrastructure code from different security perspectives simultaneously.
Exactly. And they are applying infrastructure as code graph reasoning. They aren't just reading text like a linter. They are building a mathematical map of your entire AWS environment in memory.
That's wild.
They can trace complex network exposures or deeply buried identity and access management drift way before that Terraform code is ever applied to production. And if it finds a flaw, the AI automatically generates a pull request with the fix attached.
Okay, that proactive approach is huge, and it actually ties into a massive pain point. The sources address the dreaded 3 a.m. on-call alert.
Oh, we all know that one.
Right, we've all been there. You get paged, you open your laptop, and you're staring at an explosion of logs trying to understand a microservice you literally haven't touched in a year. The Run LLM source brings up a fascinating point. The 3 a.m. crisis is rarely a technical issue at its core. It's a knowledge management problem.
Especially in highly distributed remote teams. I mean, no single engineer holds the entire system context in their head anymore. It's impossible.
Right. And AI is uniquely suited to solve that exact context gap. Instead of a groggy engineer digging through wikis, the AI instantly pulls the recent commits, correlates the specific log spikes, reads the existing runbooks, and just presents a plain English summary of what broke.
And who changed it last, and what the immediate rollback steps are.
Yes, it's brilliant.
And it actually goes a step further than just summarizing alerts. AI is now capable of refactoring highly complex core logic at scale. The mixed panel use case in our data is a standout example of this.
Oh, I read about that. They were having issues with their database compaction pipeline, right?
Exactly. They were struggling with a pipeline that kept throwing out of memory, or O, errors. Their original code used a static crude multiplier to estimate how much memory a compaction job would require.
Which basically means it was guessing. And when it guessed too low, the server crashed.
Yep. The logic was flawed, but it was deeply embedded in their systems. So they utilized AI-assisted analysis to parse through massive amounts of operational data to find a better heuristic.
And what did it find?
The AI helped them refactor the code to use a last observed value approach for memory estimation instead of a static multiplier. The result of that single AI-assisted refactor was a 99% reduction in their median memory estimation error.
99%.
They practically eliminated an entire class of reliability failures.
That is a brilliant application. But, I mean, having fleets of AI agents auditing Terraform, synthesizing 3 a.m. alerts, and refactoring database pipelines brings up the trillion-dollar issue. The inference tax.
Ah, yes. The cost.
Compute is not free. It's like hiring a team of genius PhDs, but making them use $500 a cup artisanal coffee just to write a basic docstring. Paying an advanced LLM to analyze every single log line is financial suicide.
It really is. The industry is finally recognizing that utilizing a massive frontier model with 2 trillion parameters for a trivial task is incredibly wasteful. It's a massive resource drain.
That's where the concept of inference routers comes into play. I'm looking at DigitalOcean's integration with OpenCode, which, by the way, is a massive AI coding agent on GitHub with over 160,000 stars.
Yes, it's huge.
They aren't just blindly sending requests to the most expensive model. They built a router that dynamically analyzes the incoming developer prompt.
Right, so it routes based on complexity.
Exactly. If it's a complex architectural query, it routes it to a heavy model. But if the developer is just asking to format a JSON file, the router silently redirects that task to a smaller, hyperfast open source model.
It dynamically optimizes for latency, cost, and output quality on a per-task basis, which is so smart. And AWS is taking a similar granular approach with Bedrock. They recently launched GPT 5.5 and GPT 5.4 alongside the Codex coding agent, which is already used by over 4 million developers.
Yeah, and what I found crucial there is their shift to a strict paper token model with 0 per developer seat licenses.
Yes. You literally only pay for the exact compute your orchestration requires. And they are physically restricting heavy workloads like GPT 5.5 to massive data centers in regions like US East and Ohio just to manage the sheer power requirements.
While GPT 5.4 is globally prioritized for cost efficiency.
Exactly. But even with smart routing and localized capacity, the physical hardware layer was still buckling under the sheer volume. If we connect this to the bigger picture, the most profound cost savings are actually coming from bare metal optimization.
Okay, tell me more about that.
DigitalOcean, partnering with a company called Infract, managed to slash their AI inference costs by up to 4x using a technique called prefix-aware routing and caching within the VLLM engine.
Let's break down the mechanics of prefix caching because it is brilliant. Every time an LLM processes a prompt, it has to compute the mathematical attention matrices for every single word.
Right.
If you have a system prompt that contains 5,000 words of strict coding guidelines, which is the prefix, the GPU has to crunch the math for those 5,000 words before it even looks at the developer's actual question.
And if 10,000 developers are hitting that same agent, you're paying for the GPUs to calculate that exact same 5,000-word math problem 10,000 times a minute. It's terribly inefficient.
So prefix caching intercepts that. It calculates the mathematical representation of that system prompt once and physically stores those key value tensors in the GPU's memory.
So it doesn't have to do it again.
Right. The next time a request comes in with that same prefix, it completely skips the computation phase and just pulls the math right from memory.
And to make that possible at an enterprise scale, they're deploying absolute behemoth hardware. They are running massive AMD Instinct MI325X GPUs boasting 192 gigabytes of memory, and NVIDIA H200s with 141 gigabytes.
That is a ridiculous amount of memory.
By holding those massive prefix matrices in that expanded memory pool, they actually increased their cache hit rates from 25% to over 75%. On a volume of 10 million daily requests, that single memory optimization recovers up to 340 GPU hours every single day.
340 hours of raw compute saved daily just by remembering the math. That is exactly how you survive the inference tax. But here's where it gets really interesting, because all these autonomous AI agents, routing models, and prefix caches require perfectly reliable underlying infrastructure.
None of it matters if the servers don't turn up.
Exactly. If the metal breaks, the AI pipeline is dead in the water. And looking at the non-AI DevOps advancements in our sources, there is some really gritty, bare metal engineering happening right now.
The foundational layer cannot be neglected. A brilliant example is the recent Cloudflare incident from the sources. They actually managed to reduce the server boot time across nearly 2,000 core machines from a crippling 4 hours down to just 3 minutes.
When I read that, it blew my mind. I mean, going from 4 hours to 3 minutes at that scale is a monumental engineering feat, and the mechanism behind the delay is fascinating.
There's a firmware issue, right?
Yeah, a routine firmware update essentially confused the servers. Upon booting, each server would spend roughly 20 minutes uselessly probing failed or disconnected network interfaces via the pre-boot execution environment before finally stumbling onto the correct interface to actually boot from.
And you multiply 20 minutes of dead probing by thousands of machines rolling through a reboot cycle, and your entire deployment window just evaporates.
Totally. To fix it, Cloudflare engineers had to bypass the automated sequence and explicitly declare the correct network interface up front. But it wasn't easy. It required battling lazy-loaded UEFI data structures, reverse engineering vendor-specific naming conventions that didn't even match the documentation.
Of course they did.
And overriding supposedly immutable firmware settings. It is a stark reminder that no matter how advanced our AI gets, someone still has to know how the motherboard boots.
That same drive to remove foundational friction is really visible in data management, too. Databricks recently rolled out a feature for their lake-based product called copy-on-write database branching.
Oh, this is huge for testing.
Historically, if a developer needed a copy of a massive production database for testing, you had to physically duplicate terabytes of data, which took hours and doubled your storage costs.
But with copy on write, Databricks doesn't actually duplicate the files, right? It creates a lightweight metadata pointer in exactly 1 second.
Yep, just 1 second.
Both the production system and the developer's tested branch point to the exact same underlying storage files. It is only when the developer makes a write, like when they change a specific row of data, that the system allocates new storage specifically for that tiny change.
Which means every single developer in an organization can instantly provision their own isolated production-scale database environment at virtually zero initial storage cost. It entirely eliminates the bottleneck of shared staging environments in CI/CD pipelines.
That's game-changing. And the broader ecosystem is ruthlessly shedding legacy weight to maintain this kind of velocity. NixOS just released version 26.05, codenamed Yara. They merged over 20,000 new packages.
Wow, 20,000.
Yeah. And they finally standardized on system-based stage 1 booting by default, bringing much-needed consistency to the boot process. But the massive news there is that they are officially dropping support for the 86664 Darwin architecture.
Well, due to Apple's complete platform deprecation of Intel chips, The NixOS maintainers really had to make the hard call to cut the cord. It's a necessary shedding of technical debt.
Definitely.
At the same time, orchestration layers like Kubernetes are taking on heavier workloads than ever before. The sources detail enterprises using crossplane within Kubernetes to declaratively provision Azure PostgreSQL flexible server databases.
Oh, so they are achieving multi-region, active, passive, high availability for relational databases, but completely abstracted behind Kubernetes APIs.
Exactly, while maintaining brutally strict private networking.
Speaking of strict networking, we have to look at the insights on air-gapped systems. In highly secure, air-gapped environments, there is a literal physical or cryptographic separation.
Right, developers absolutely cannot just SSH into a pod to check logs or debug a live issue. Right.
They basically throw the compiled code over a highly restricted wall. So if a microservice crashes in production, the on-prem operator, who has zero context on the actual business logic, has to somehow detect and fix it.
Which is exactly why service-level indicators, or SLIs, have to be engineered completely differently in those spaces. Developers must build structured, highly descriptive self-service tooling and codify their errors perfectly.
So observability in an air-gapped environment isn't just installing a monitoring agent.
No, not at all. It is an organizational strategy of transferring operational ownership without transferring code access.
That organizational strategy angle perfectly tees up the final piece of our puzzle today. The State of Observability in FinTech report. The data shows that financial services are actually leading the charge right now, hitting 70% maturity in their observability practices.
That's impressive for such a regulated industry.
It is. They are heavily standardizing on open telemetry, and an astonishing 94% have adopted generative AI in some capacity. But there's a massive irony buried in the report.
I noticed that too. They are enthusiastically using AI to monitor their traditional infrastructure, but their tools for monitoring the AI itself are severely lagging.
Exactly. Observing traditional microservices is relatively easy because code is deterministic. If function X receives data Y, it prints out log Z. If it crashes, you check the stack trace.
It's predictable.
But observing an LLM in production is entirely different. It's less like monitoring a machine and more like managing a highly creative, slightly erratic employee.
That's so true.
You can't just look at the crash logs. You have to evaluate the nuance, the latency, and the logical accuracy of its decisions in real time.
We have essentially handed the controls of the aircraft over to an autopilot that we only partially understand. And right now, our dashboard doesn't have the right gauges to monitor the autopilot's decision-making process yet.
Bringing this massive stack of sources back to you, the listener, what does all of this mean for your day-to-day work?
Well, the central takeaway is that your role as a technologist is permanently shifting.
It's an entirely new paradigm. You are no longer just a typist of code blindly hammering out boilerplate. You are an orchestrator. You are a validator. You are a boundary setter. You are designing the testing frameworks and architectural guardrails for autonomous systems that are incredibly powerful, yet, as we've seen, prone to hallucinations and exploitation.
This raises an important question, and it is the puzzle I want to leave you to mull over today. We are accelerating toward a reality where one AI agent writes the application code, a parallel AI agent audits that code for security flaws, and an AI inference router mathematically dictates which hardware model will execute the task most efficiently.
All of it running on self-healing, copy-on-write infrastructure.
Exactly. So when that loop is fully closed and automated, what becomes the true bottleneck of human innovation? Is it simply waiting for bigger GPUs to compute larger prefix caches? Or will the only real bottleneck left be human imagination and our ability to ask the right questions?
That is the perfect, provocative thought to end on. Thank you for joining us today to cut through the information overload. We really hope you leave this deep dive feeling a bit more armed with the technical mechanisms, a lot more curious, and ready to orchestrate whatever challenges come next. Keep pushing boundaries, keep asking the hard questions, and we will catch you on the next deep dive.
Spoken Tech for your ears.